In this series of videos, we are going to explore flow kinematics and Bernoulli's equation. At the end of this section, you should be able to describe fluid motion in multiple frames of reference. You'll be able to describe flow features mathematically and interpret their physical significance. And finally, you'll be able to apply Bernoulli's equation and understand its limitations. You'll also know where Bernoulli's equation comes from, which you will soon see that it is the application of Newton's second law along what is called a streamline. So first, we're going to talk about the fluid velocity field. Recall from the continuum hypothesis that any fluid property, such as temperature, velocity, pressure, etc., can be described as a function of the fluid's location in space. That is, we are not concerned with the atomistic nature of the fluid itself. If we were to consider a volumetric cube of fluid, we could divide that fluid up into smaller and smaller and smaller pieces infinitely many times. This is what the continuum hypothesis is saying. This hypothesis predates atomic theory. But what we have found is that it is actually quite useful and accurate in fluid mechanics, in solid mechanics, especially when we're looking at these fields in a relatively large scale. So this representation is called the field representation. Okay, so where we're saying that a fluid property such as temperature, pressure, velocity can be expressed as a function of x, y, and z. The field, whether that be a scalar field, a vector field, it can change with time. A scalar field would be something like temperature as a function of space and time. So you can think of the temperature in the room where you're watching this video can be defined at any point in space. And the temperature at a particular point in space can also change with time. This is what this field representation is saying. We also have vector fields. So vector fields would be things like, well, the velocity field is the most intuitive one, where we have the velocity in the x, y, and z directions defined by the u, v, and w components of velocity respectively. And as we can see, each component u, v, and w can be described as a function of the spatial coordinates and can also evolve with time. Recall that for a vector, it is defined by both a magnitude and a direction, and its magnitude can be found by taking the square root of the summation of the squares of each velocity component u, v, and w. So let's consider how we would study a flow. Now, when we looked at control volume analysis, we kind of touched on this a bit. We have two options when seeking to study a flow. We can either follow a particle as it evolves, as it travels through space, or we can observe the behavior of the flow at fixed points in space, such as an area or a volume. And recall that with control volume analysis, this is precisely what we want to do. We want to look at a defined region in space, and it is defined by x, y, and z, and see what happens in this region. Whereas in the alternate description of a flow, we are actually just following a single particle or a group of particles. And this is the distinction between the Eulerian and Lagrangian descriptions of the flows. So the Eulerian description of a flow is the observation of the behavior of the flow at fixed points. So this can actually just be a point, an area, a volume in space. And so this Eulerian description is very much very similar to what we looked at with the control volume analysis. Whereas the Lagrangian description is the tracking of individual or a group of particles as they travel through space. So the tracking of individual or groups, individual particles through space. And the difference between the Eulerian and the Lagrangian description is precisely the dilemma that we encountered when looking at control volume analysis. Recall that our conservation laws, they apply to a particle or a group of particles. So this is very much a Lagrangian description. But with control volume analysis, we want to observe a volume in space. That's an Eulerian description. So what we looked at in control volume analysis is the Reynolds transport theorem, which reconciles both of these descriptions, with the left-hand side of the Reynolds transport theorem being in a Lagrangian frame of reference, and the right-hand side being in an Eulerian frame of reference. So how would one accomplish these two descriptions of how to study a flow in practice? So in a lab experiment, for example. So in the Eulerian description, we could study it in this manner by setting up probes in space. So for example, a pressure sensor at a fixed location. There are other things, like we have things like hot wires. Hot wires, they are ways to measure the local velocity vector, and typically these are at fixed points in space. We could set up thermocouples, and again, these are temperature sensors, which would be at fixed points in space. Okay, so these are not tracking individual particles. In the alternative, we could tag individual particles. And we could do this using, dyes. We could use a smoke wire. And so what this does is that as the flow passes, let's say, past a certain point, we inject a dye, so that dye tags that particle, and then we observe that particle as it evolves through space. In practice, it is much harder to follow individual particles in space. The Eulerian method is typically preferred both analytically and experimentally, although some situations or studies are better described in a Lagrangian frame. All right, so let's look at an example here. So let's assume that we have a chimney. So we have, we have the exhaust from the chimney escaping like this. We can consider the temperature of the exhaust as the variable of interest. Okay, so what we would do what I'm going to do is on the left-hand side of the chimney, I'm going to show a Eulerian description. And on the right, I would show a Lagrangian description. So I'm going to clean this streamline up here. So in a Lagrangian description, what we would do is that we would have, let's say over here, particle A. And so let's just make sure that we define it here. And this path here is the path that is traced by this individual particle, A. So it is the same particle. So we followed this particle. Perhaps we've injected a dye there or something like that. And so this is the Lagrangian description. Okay. So we're following an individual particle. Now in the Eulerian description, what we would do is that we would have a coordinate system, and we have the exhaust of the chimney stack. And what we would do is we could just simply define, let's say at this point over here, we could call this x1, y1. It will have an associated temperature at this particular location. So we would have a temperature over here, which is a function of x1, y1, and defined at a certain time. We could probe another location. We could call this x0, y0. And over here, again, the field at that particular location will be defined at x0, y0, and t. So on the left-hand side, which is the Eulerian description of the flow, we are not tracking individual particles. Rather, we are just probing specific locations in the flow. And so that specific location in a flow, let's say at point x0, y0, will be traversed by different particles at different points in time. Okay, so let's dive into these Eulerian and Lagrangian concepts a bit more. We're going to discuss here pathlines, streaklines, and streamlines. These are methods to visualize and analyze the flow. And these are kinematic concepts. So if you recall from your study of dynamics, kinematics is a geometric description of the flow. It seeks to describe the motion of whatever body you are analyzing, a particle, a rigid body, without regard to the forces that have caused this motion. Okay, so these pathlines, streaklines, and streamlines are kinematic concepts. They are descriptive of the motion of the flow. So, what is a pathline? A pathline is the path traced by a single particle over some period of time. Okay, so this is very much our Lagrangian concept. Okay, so you could imagine we are just at a certain point in time, we're going to inject a dye, and then we're going to see that particle evolve through time. A streakline, on the other hand, is the line connecting all fluid particles having passed through a single point over a period of time. So it's very close to a path line, but again, we are not observing an individual particle, but rather it is the line connecting all the fluid particles that have passed through a single point. And so how we would achieve this is, for example, by continuously injecting a dye at a single point. Whereas in a path line, we might just inject the dye for a very short period of time. So let's sketch this out so that we see the difference between a path line and a streak line. So what we're going to do, we're going to consider a point P over here. And this will be the point where we're going to either inject a dye or maybe have a smoke wire. So a smoke wire, if you're not familiar with the concept, it's a heated wire and it might have some oil on it. And so as the flow passes over that wire, and again, it's heated, you're going to get some smoke that convects away from that smoke, that heated wire. Okay, and it's just another way of visualizing the flow. So let's look at a path line. So over here, let's say we could have particle A at T naught. Okay, so at a certain time, we have a particle, which we will call particle A, which passes through point P. So recall the path line is a path traced by a single particle. So this path line here would be the curve describing that same particle. So here, this would be particle A, and so this could be at T1, which is at a time greater than T naught, where it originated. Over here, so this is again particle A, but here it's at T. This could be another time, let's call it T2. And then, particle A here, particle A at T3, and again, this is greater than T naught. Okay, so this is the path followed by a single particle. Okay, I think this is fairly intuitive. You could think of a particle as, just like, let's say, you could think of this being a car, and this is the route that the car took between time T naught and time T3. Okay. On the other hand, so let's draw a streak line. So here, let me just annotate this over here. So this one above here is a path line. Okay, so let's look at a streak line. So recall, the streak line is the line connecting all fluid particles having passed through a single point. And in this case, that single point is point P. So these three dots are actually different particles. And the yellow line is the line connecting these different particles, which all have passed through point P. So if you were to look here at, let's say, a particle B, and we could say this was at P at some time. And that would be at some time, T naught less than T less than, let's say, our final time under consideration, T3. Okay? So this is the distinction between a path line and a streak line. Okay, so a streak line, you can consider, let's consider point B. Let's use our car analogy again. So point P could be a certain intersection on a street. And you have many cars that have passed through that intersection. And the streak line would be some curve that connects all of the cars that have passed through that certain intersection. Okay? Finally, we look at the streamline. Now, arguably, the streamline is the most useful concept in fluid kinematics. Okay? So, the streamline is a line that is tangent to the local velocity field everywhere along its length. And again, because the fields, the velocity field can evolve with time, so we should say that this is at an instant in time. So at a subsequent time, the streamlines may look completely different depending on the nature of the flow. So let's sketch this out, and hopefully it'll be a bit more intuitive what we mean by a streamline. So let's consider an airfoil. Okay. Now, our airfoil, and again, this is at a single snapshot in time. Okay, so these are the velocity vectors. So we're not following a single particle here. So this is the velocity field. At a single point in time. And here, just for fun, I'm going to draw a little, what we call a recirculation bubble over here. Here we have what is called our stagnation point. And down here, we have what is called the pressure side of the airfoil. Now, this is not a very good sketch, but I think it will do for our purposes. Okay, so these are the velocity vectors. So for example, here, again, we are not looking at individual particles. We're taking a snapshot in a certain area or volume of space. So this is, let's say, x naught, y naught. This would be over here, x n, y n. And so this is composed of many particles over here. So at this point, at x naught, y naught, the particle over there has a certain velocity vector. At point xn, yn, the particle that is occupying that particular point has a velocity vector in a certain direction and with a certain magnitude. So the streamline is therefore the line that is tangent to the local velocity field. So the local velocity field over here, we have a line over here, a line over here, a line over here. And so everywhere along this particular streamline, it is tangent to the local velocity field. And so this is all a single streamline. We could call this streamline 1. Okay. And so over here you'll have another streamline, and down here you have another streamline. Okay, so a streamline is a line that is tangent to the local velocity field everywhere along its length. So everywhere along the length of streamline 1, it is locally tangent to the velocity field. Okay? And again, I want to emphasize that this is at a single point in time. So this could be defined at time t1. At time t2, the velocity vectors could be in a completely different configuration, especially if we have an unsteady flow. Okay? And therefore, the streamline patterns will be different. And here's a nice distinction, or a nice nuance about all of this, is that for a steady flow, then the path line is equal to the streak line and is equal to the streamline. So they are all the same, they all collapse onto each other for a steady flow. And again, a steady flow is one that is not changing in time. So if we're looking at this airfoil flow over here, then the velocity vectors are always going to be in this same configuration at all times. Okay, that would be a steady flow. Okay, and so you can imagine if we were to be introducing a die at this point over here, then a path line would just follow the streamline as it evolves through time and space. Okay. All right. So we're going to wrap up this video by just recapping what we have done. We have come up with a distinction between the Eulerian and Lagrangian descriptions of fluid flows. The Eulerian description is one where we look at particular points in space, okay? Whereas the Lagrangian description is one where we track individual or groups of particles. We looked at a few kinematic concepts, which are the path line, the streak line, and the streamline. And we have found that for a steady flow, these three are equal to each other. In the next video, we're going to see how we can come up with mathematical expressions for streamlines and pathlines.